In this video, we want to continue looking at chemical reactions. Next, we want to look at what can influence the reaction rate in a chemical reaction. The answer is there are three main things that can influence it. The first is concentration, the second is temperature, and the third is the presence of something that are called catalysts, which we'll talk about in a minute. But here's the basic idea. I have some chemicals that I want to combine. So I have the reactants, they undergo a chemical reaction and they produce products. How fast does that process occur? These are the three things that can affect how quickly that process is going to occur. Now, in order to understand what's going on in this process, we have to start with a premise. And our premise is that the reactant molecules have to make physical contact with each other in order to transform into products. In other words, let's say that I have some hydrogen and some oxygen. Now, the first thing that can affect this is concentration. And so if I look at these two boxes, imagine these are two boxes containing some gases that are combining. So here I've got N2, which is nitrogen, and O2, which is oxygen, and they're going to combine and form nitrogen monoxide, which is NO. So what's going to happen here in a situation where the original gases are less concentrated, they're not going to bump into each other as much, and so they're going to have fewer opportunities to undergo that chemical reaction. Whereas if I have a lot more molecules in the box, in other words, it's much more concentrated, they're going to bump into each other much more frequently. There are going to be more opportunities for that chemical reaction to occur, and that means that the reaction is going to occur more quickly. So the result of this is more concentration means faster chemical reactions. The next thing that can influence the reaction rate is the temperature. Now, basically what happens with the temperature is this. Temperature relates to how quickly the atoms and molecules are moving, whether they're moving around the room or the box like a gas, whether they're vibrating back and forth like in a solid or a liquid. The rate at which they're moving, the speed with which they're moving, depends on the temperature. And so higher temperature means faster motion. The higher the temperature, the faster they're moving. So let's consider the situation where they're not moving very quickly, when they're moving slowly. And so these molecules are moving slowly, they get closer together. When they finally meet, they don't have a lot of energy when they bang into one another. There's not really enough energy to initiate that reaction, so they just kind of bump off and go their merry way. They don't have that chemical reaction because there's not enough energy. Now, we can contrast that to the situation where imagine these guys were coming in more quickly. When they finally collide, these guys are moving very fast, and there's actually enough energy to cause these atoms to separate so that they can recombine. And so higher temperature means more opportunity for reactions. The third thing that can affect the rate is the presence of a catalyst. Now, before I talk about what a catalyst is, let's talk about the normal process of a reaction. So here I've got some nitrogen and oxygen molecules, some N2 and some O2, and they're going to form nitrogen monoxide, NO. Now, in order for that to happen, these guys have to be coming together with enough energy to be able to break these molecules apart so that they can recombine. That is called the activation energy. And so this reaction requires this much energy for this reaction to occur. If you have these guys coming together with less than the activation energy, they're not going to undergo that chemical reaction. And so we can see reactant molecules must gain a minimum amount of energy called the activation energy each in order to transform into the product molecules. Now let's look at another example of this. We've got ozone, which is the O3 molecule, transforming into oxygen, normal oxygen, the O2 molecule. And so the reaction is 2 ozone molecules will yield 3 oxygen molecules. And just like we were describing in the slide, so I've got these 2 ozone molecules coming together. It requires a certain amount of activation energy to initiate the chemical reaction, and then after the reaction, you end up with 3 normal oxygen molecules. And so if you don't have this much energy, you're not going to get that reaction. Here's where a catalyst can come in and help you, though. If you have a particular catalyst, what the catalyst does is it allows intermediate chemical reactions to occur, each one at a lower energy. So in the end, you get the same results as the previous reaction, but it requires much less energy. And so here you can see the reaction. I've got 2 ozone molecules with the presence of chlorine, and you can see the chlorine here over the yield symbol, and that leads 3 oxygen molecules. The presence of chlorine, it acts as an intermediary in that reaction, and it lowers the amount of energy necessary for the reaction to occur. That means more opportunities for the reaction are going to occur, and the reaction will happen faster. Okay, so now let's look at an example. I've got ozone, O3, that I want to form from molecular oxygen, O2. And so this process occurs as follows. I've got O2 plus 2NO, and that forms 2NO2. That's one of my intermediary reactions here. And so now I've got 2NO2, that forms 2NO plus 2O. And then my 2O combined with my 2O2 to form 2O3. And so the question is, what is acting as the catalyst here? And the answer is, we're adding in the NO to the regular oxygen, and that is facilitating the transformation of O2 into O3. So the NO is our catalyst. And so this would be B to give us our answer. Now, one of the features of catalysts is that you always end up with the catalyst when the reaction is done. In other words, let's look at this process again. So I've got O2 plus 2NO, which is our catalyst, and that forms 2NO2. But that 2NO2 breaks down and we get our 2NO back, plus the 2O. Now these 2O combine with our O2, so it takes for every 2O, it'll combine with 2 of the O2s to form our ozone, the 2 ozone molecules. But this NO2 is still hanging around. So I input NO as my catalyst, I still have the NO left over. That's a feature of a catalyst in a chemical reaction. So you input this catalyst to help the reaction speed along, to require less energy in the reaction, and the catalyst will temporarily change into something else, but it always ends up in the final product that you have some of the catalyst, that catalyst is restored. Now the next thing that we want to talk about is the difference between what is called an exothermic reaction and what's called an endothermic reaction. With an exothermic reaction, what you have is a chemical reaction where you combine some reactants and you end up with some products, but the process of the reaction releases energy. So very often that would be in the form of heat. So you could imagine that I mix 2 chemicals together, they have a chemical reaction, they transform into something else, but what you end up with gets heated up because in the process of that reaction, some of that heat energy is released into the solution and warms it. And so this is an exothermic, thermic, T-H-E-R-M, that's a root word meaning heat, like, thermal underwear is underwear that holds heat in. Exothermic reaction is one that expends heat or causes heat to go out. Now, an endothermic reaction is one that takes in heat or causes heat to be absorbed. And so this is a situation where you have some reactants that you mix, but they're not going to form a chemical reaction unless you add some extra energy. And so I add this energy, the energy goes with the reactants to create the chemical reaction. Now, An example of this is what can happen is you could actually mix two chemicals together and they combine and form something else, but in doing so, they actually absorb energy in the process of the reaction so that the reaction cools off. So instead of giving off energy, they absorb energy. And so in an endothermic reaction, what you can end up is that the reaction occurs, and in the process of going through the chemical reaction, the reactants actually absorb energy from their environment and cool it off. And so what you end up with is energy is absorbed during the reaction rather than energy being given off. So that's exothermic, where energy is given off, and endothermic, where energy is absorbed. Here we see a very important table, and you might want to print this table off. I'll put a link to it in the modules. It might be useful for some of your homework, but this particular table is showing various bond energies. And so, for example, hydrogen 2 consists of two hydrogen atoms that are bonded together, and in order to bond two hydrogen atoms together, it takes 436 kilojoules per mole. So for every mole of H2, 436 kilojoules of energy have been expended. And joule is, of course, just a unit of energy, and kilo means 1,000, so a kilojoule is just simply 1,000 joules. So let's look at an example here. We want to have a chemical reaction, so we've got hydrogen 2 and chlorine 2, so we've got H2 and Cl2. They're combining and they form 2 HCl. And the question is, using the bond energies provided, and they're provided over here, we want to determine whether the following reaction is exothermic or endothermic. And all of these are asking with regards to being 50 kilojoules of energy. So the possibilities are exothermic with more than 50 kilojoules of energy released, endothermic with more than 50 kilojoules of energy absorbed, endothermic with less than 50 kilojoules of energy absorbed, or exothermic with less than 50 kilojoules of energy released. So the answer is that this reaction is exothermic with more than 50 kilojoules of energy released. How do we know that? How are we going to be able to figure that out? Well, let's look at each of these energies. We have 436 kilojoules per mole of energy. So for every mole of H2, we've got 436 kilojoules of energy. So for this guy here, we would have 436 kilojoules of energy. For the chlorine, the Cl2 molecule, that chlorine-chlorine bond gives 243 kilojoules per mole. So the energy for every mole of chlorine, that's how much energy, the energy of the hydrogen plus the energy of the chlorine, that's how much energy is on the left-hand side. Now, on the right-hand side, you've got two HCl bonds. And so the HCl bond energy is 431 kilojoules per mole. And of course, we know that HCl stands for hydrogen chloride, according to our naming convention. Oh, and just FYI, HCl, hydrogen chloride, is normally a gas, but if you dissolve that gas in water, it turns it into an acid called hydrochloric acid. And we'll talk about acids and bases later on in the semester, but just as an FYI, that HCl is hydrogen chloride. Anyway, let's look at these energies again. So on the left-hand side, we have 436 kilojoules per mole plus 243 kilojoules per mole. That gives us a total of 679 kilojoules per mole. Now, on the right-hand side, we have two hydrogen chloride molecules. Each one of them has 431 kilojoules per mole. So if you add them both up, you get 862 kilojoules per mole. And so you can see these guys add together here to give you that much on the left-hand side. So that means that in the process of this chemical reaction, the hydrogen and the chlorine combining together, 679 kilojoules per mole are absorbed to make that reaction. Now, when the products are formed, we have 862 kilojoules per mole released. So that means that there's actually an excess of energy over on the right-hand side. And so if you have two things reacting and they make products with extra energy, we know that's characteristic of an exothermic reaction. So that's how we know the reaction is exothermic. The next thing we want to understand is how do we know that more than 50 kilojoules of energy will be released? Well, we just take the numbers. We know that this is 862 kilojoules per mole. That's on the right-hand side. We compare that to 679. We know that the excess is going to be on the right-hand side, and the difference is just 862 minus 679, and that leaves us with 183 kilojoules per mole. That's the amount of energy released. And of course, 183 is bigger than 50. If the answer had been 22 or something smaller than 50, then the answer would have been one of the other options. But clearly, this is an exothermic reaction with energy being released in excess of 50 kilojoules. So that is all you need to know to answer the question. Now, the next thing that we want to talk about is entropy and how entropy relates to the rates of chemical reactions. It turns out that chemical reactions are in fact driven by this thing we call entropy. So what is entropy? The truth is that when physicists talk about entropy, there are some very sophisticated equations involved that are well beyond the scope of this course. But the basic ideas that result from the application of those equations are pretty easy to understand. And so that's kind of the level that we're shooting at here, understanding conceptually what entropy means and what its consequences are. So one way that we can define entropy in a simple way is to say that it is simply a natural tendency of energy to disperse from where it is concentrated to where it is dilute. So here we have an example of entropy. A hot pan radiates heat. The energy is concentrated in the pan and it's radiating out into the room. It's dispersing. And that is just a tendency of things in nature. Another example is gasoline combusts into smaller molecules. Basically, you have fewer large molecules and they break into more pieces which consist of smaller molecules. And so you have this sort of dispersion of from big molecules into smaller molecules, and that has increased the entropy. Another example is marbles bouncing on the floor. They don't bounce forever. The energy kind of, basically every time the marble bounces, some of that energy gets converted into heat and disperses into the room. And so that means that energy is no longer available for that ball to keep bouncing. That's why every time the ball bounces, it bounces a little bit less high than it did the previous time, and it just sort of dies out. And all the energy that the balls had when they were bouncing has been sort of turned into heat, which is just spread out through the room. So in the context of the chemical reactions that we've been talking about, entropy is a term that's used to describe the degree to which energy has become dispersed or spread out. So reactions that result in an increase in entropy or energy dispersal, those are the kinds of reactions that tend to occur on their own. So which type of chemical reaction leads to a greater dispersal of energy? Exothermic or endothermic? Pause the video for a second and think about it. Which do you think? No, really, pause it for a second and think about it. Try to guess what the answer is. Did you guess exothermic? Because that would be the correct answer. Exothermic because why? In an exothermic reaction, the reaction causes energy to be given off, hence dispersed into the environment. And so that's the kind of reaction that's going to lead to a greater dispersal of energy. Now, the other thing we can think about is that this means that exothermic reactions tend to be self-sustaining because they lead to large increase in entropy. The endothermic reactions, you have to supply energy into them to make them work. But the exothermic reactions actually give off energy, so that's why. Now, an exothermic reaction is one that tends to be self-sustaining because they lead to larger increases in entropy. An example of an exothermic reaction is a campfire. You're burning wood or some other material, creating fire, and as that wood is combusted, it's giving off heat and light, and that energy is what's given off in those chemical reactions. And it's self-sustaining in the sense that if I have a pile of wood and I set it on fire, as long as there's fuel to burn, it's going to keep burning. It's self-sustaining. Now, another kind of reaction is, of course, an endothermic reaction, and they tend to require the continual input of energy. They'll stop working if you stop putting in extra energy. An example of that is photosynthesis, which is, a chemical reaction where plants transform sunlight from the sun. The plants take the sunlight from the sun and they absorb that energy and use it to create chemical reactions to essentially make food. But of course, if you take away the sunlight, if you put the plant in a box and don't allow it to have access to sunlight, it won't be able to sustain that reaction and it'll die. Because the process of photosynthesis requires that continual input of sunlight, you can say that that's why it's an endothermic reaction, not an exothermic reaction. So hopefully all that makes sense, and I will leave you with those final thoughts.